Okay, so here's a fun little example that I like for using hypothesis testing. So the data set we're working with is professor salaries. I believe it's at a public university in Michigan. And what we see is when we do a group by sex, we're looking at male and female professors and their salaries. We see that on average, females are making just over 100,000 and males are making 115. So the situation is you show this to a friend and you say, oh, look, females make less than males. Like, this is not okay. But then your friend responds back with, I mean, if you look at those values, they pretty much make the same. And I mean, look, there's not a lot of observations. Like, this is probably just from random chance. Like, I don't think there's a real difference. So the question is, how do you show that your results are significant, that there actually is a difference? So what we end up doing is we end up simulating a world where the male and female professors do make the same. So how do we do that? Notice here, we took the individual means from the female and male columns. But what we can do is create a bunch of random data where the males and females do have the same mean and standard deviation. You may ask, why would we do this? Well, if we do this, say, 1,000 times, where we create some random numbers, but with the same mean and standard deviations, and then check their difference, what we can do is plot that difference on a histogram. So I hope it makes sense that if we plotted the difference between male and female salaries, assuming they have the same mean and standard deviation, we would see our histogram centered at 0, where there is no difference. And what we can do now from this histogram is ask, how likely is it that we will see a difference like we did in our original data of $14,000? If we look here, 14,000 lies about right over here. So it looks pretty rare. And let me restate. What we're saying here is if the male and female professors make the same amount of money, what is the likelihood that we would see the data we observed up here? So we can do this with percentiles on this histogram. Like, we did 1,000 simulations. What percentage of them showed at least that difference? When we do a 95 percentile, we can see the max is 9,000. Our original mean was around 14,000. So to reiterate, what that is saying is under this simulated world where they make the same income, less than 5% of the time do we see a difference like we observed in our data. We do this again, but with a 99% confidence. So once again, what this is saying is under this simulated world where they make the same, the likelihood that we would observe this difference of 14,000 isn't even captured yet. So in less than 1% of our simulations where they have the same income, do we observe data like we saw here? Okay, so what was the point of all this? So you may commonly hear the wordage like a 95% confidence interval. So in this case, what we can say is we reject our null hypothesis at the 99% confidence interval. That is, we reject the idea that male and female professors make the same with 99% confidence. And that is because in our simulated world where they make the same, we see the data we observed here less than 1% of the time. That is to say, it is very rare that you would see this data if male and female professors made the same income. That's hypothesis testing, or at least one example.